Hey kids, welcome to day 2 of section 9.1 in our textbook. Remember yesterday we did counting, or the last video we did counting and permutations. And we kind of messed around, and did a couple variations of each of those, right? But remember, permutations or arrangements was where you were filling slots with choices. And I really didn't need my permutations unless I had less slots, my permutation formula, unless I had less slots than I had choices. So today we're going to be talking about moving from those permutations, right, arrangements, to something called combinations. So first, let's just start off. I'm in a rental unit. We're going snowboarding, and there's a table in the rental unit, but there's only 3 chairs. So when the kids are sitting down, 6 kids, only 3 of them can sit at the table. The other 3 have to sit on the couches. How many choices are there? So from yesterday, we would say, well, there was 6 kids, but only 3 chairs. So we would fill out our formula and we would say 6 times 5 times 4 times 3 times 2 times 1 would be the arrangements of the kids, but we would divide off we didn't want any repeats, right? So we would divide off those groups. So again, the numerator is the total arrangements of the 6 kids. The denominator is on the fact that I only had the 3 slots, the 3 chairs. But what about this question? What if I just wanted to know, okay, the 3 kids are chosen, right? I don't care which one sits in which chair. So in other words, if Dean, Deanna, and Drew ended up sitting at the table, that combination is the same combination as Deanna, Dean, and Drew. In other words, when Dean sat down in one chair, he could have just as easily sat in this chair. Right? It doesn't matter. He didn't have to be stuck here. Dean was chosen, and therefore I only had 2 more to choose from. I just want to know how many combinations. Order doesn't matter. Woohoo! If I don't care the order of which, this formula gives me too many. It overcounts. It only takes out, right? It only divides. Divides make your group smaller. Right? It only divides out the groups. But now, since order doesn't matter, I also want to divide out how many combinations look the same. So I want to take my groups, right, my permutations, and I want to divide out the number of arrangements of people. Now remember, this is the same as saying permutations times 1 over the arrangements of 3 people. So look what that looks like, right? That's 1 over 3 factorial times 6 factorial divided by 6 minus 3 all factorial, which gives me 20. So I have 20 combinations of 6 kids and 3 chairs. This tells me this number, which is, right, I covered it up there with my overcounts, but it was 6 factorial divided by 3 factorial. This tells me, so those cancel out, 6 times 5 is 30, 30 times 4 is 120. This tells me that there are 120 ways to arrange these 6 kids in 3 chairs where the arrangement of Dean, Deanna, and Drew is different than the arrangement of Deanna, Dean, and Drew. Whereas 20 counts them the same, which is why it's a smaller number than 120, and to make it smaller, divide. So combinations don't overcount. It considers the repeats fine, right? So it won't double count them. So it counts ABC the same as BAC. Order doesn't matter. So how many combinations of 4 people can be selected for a committee out of 26? So think back to the previous video when I said I wanted to choose, what was it, the drama club? I wanted to choose a president, vice president, and secretary. So once I chose the president, that person couldn't be vice president. Now, when I have 4 slots, right? So I have 4 slots. We know what that means, right? I have 26 choices, but I only have 4 slots. But when I choose the people for the 4 slots, it doesn't matter which slot they go in, right? One being in position 1 is the same as being in position 2, right? Of those 4 people. So that's why you also have to divide, which is also multiplying by the reciprocal of how many of those arrangements you had. So you have 1 over 4 factorial times 26 factorial over 26 minus 4 factorial. "26 arrangements of 4 over counts when I don't care about the order." So that's what that looks like. 14,950. Now, this is kind of a cumbersome formula. It is just fine. It is just fine, but we have another way of representing combinations. We have another formula. This formula is the same, right? Why wouldn't I just name it? I want that formula to represent combinations. So instead of saying permutations divided by that 4 factorial, I'm just going to name this formula something new and turn it into my combination formula. And that's what it looks like. When order doesn't matter, the number of combinations of n things taken r at a time is called n choose r. If you look at your calculator, same place where you got the factorial, you'll notice that you have an NPR button and an N choice and an NCR. So if you hit math, arrow over to probability, you'll see that choice 2 is NPR and choice 3 is NCR. So what you have to do though is enter the N on your home screen first, then go to NCR and then enter your R. So how many ways are there to select 3 prize pencils from 20 unique pencils in Miss Gallen's prize box? Yes, she does have a prize box. When we get back to school, the first thing you want to do is go to Miss Gallen's room and say, can I have something from the prize box? Because I just spent months and months and months in remote learning and I deserve something from the prize box. She'll be so happy I said that. So if I get, for instance, let's say I have all these different colors, right? And I get a yellow, green, and blue pencil. Well, that is the same group as having a blue, yellow, green pencil. So since order doesn't matter, I say out of the 20 pencils, I can choose 3. IB really likes this alternate notation. I don't know why, and no, they don't use it for permutations. It is only to go with combinations, but is this vertical alignment in discrete math, right? Because there are other things like in vector land, we can represent vectors this way too, but that's when we're in vector land. We are in discrete math land, combinations, permutations. This notation means combination. It means 20 choose 3. So in that formula, it is your permutations formula with the extra r factorial in the denominator. Whoops, sorry, didn't want to do that. And did I write this down anywhere? Yes, I did. Okay, so again, if you were to do this on your calculator, on your home screen, you type 20. Then you go to Math 9. No, sorry, that's calculus. Math, arrow over to probability. And I always have to look at my calculator. Choice 3. And then automatically go back to your home screen and you hit 3 and you get 1140. Lots and lots of these combination problems involve dice, and cards. Probability does a lot of work with dice. So if you're not familiar with a deck of cards, at least for these tests, you should get familiar with them. There's a standard deck of 52 playing cards. How many four card hands are possible? So you think to yourself, okay, I have 52 things. These are my choices, of which I'm only choosing 4. But do I care about the order of those 4 cards, right? If you have an ace, king, queen, and jack in your hand, that is the same as having a jack, ace, king, queen. So no, order doesn't matter. Woohoo! Use my combinations formula. I don't think I wrote this down. I trust you can get on your calculator and do this, okay? You can just if you just practice the last one in your calculator, hit second enter and just change the 20 to a 52 and change the 3 to a 4. That way, there you go. How many 4-card hands are all spades? Well, all that's doing is reducing your choices. You still have your slots are 4, but you don't have 52 choices anymore. So if you don't know, there are 4 what they call suits in a deck of cards. Those are spades you see in the picture. There are diamonds, clubs, and hearts as well. So there are 4 different suits. There are 52 cards. 52 divided by 4 is 13. The next one is how many 4-card hands are there just of one suit? We'll just take your previous answer and multiply by 4. NBD. How about this one? How many 5-card hands have exactly 2 3s? Wait a second. So wait a second. I have 5 slots. 5 slots, but 2 of them I want to be 3s. Well, question. How many 3s are there in a deck of how many cards? There are 4, right? 1, 2, 3, 4. There's 3 of hearts, 3 of spades, 3 of clubs, and 3 of diamonds. So for these 2 slots, what am I going to do? I have not 52 choices. How many choices do I have? I only have 4 choices. So I have 4 choices. And of those 4 choices, how many slots do I want to fill? Right. Now, what about the rest? What about these 3? How many cards do I have to choose from? Be careful. It's not 52, is it? How many cards? I don't want any 3s in here. So how many cards do I have left? Right? I have 48 cards. And how many do I want to choose? And then what's the operation between everybody? Multiplication, right? So there is my 4 choose 2. That fills these 2 slots. Here's my 48 choose 3. That fills these 3 slots. And then, of course, I'm multiplying. I'm multiplying everybody, right? Sweet. How about the next one? 6 men, 5 women. I want a group of 4. Order does not matter, right? Because if I choose 2 guys it doesn't matter whether this gentleman goes in this slot or this slot. I choose this one, doesn't matter which one. So order doesn't matter, right? If guy one and guy folded hands and guy jacket over shoulder is the same group as guy jacket over shoulder, guy folded hands, folded arms, right? So what is that? How many, I know I'm filling 2 slots, but I'm choosing out of how many? Right. There are 6 men and I'm choosing 2 and order doesn't matter. How about the females? If I choose those 2, again, order doesn't matter. They're going to fill in those 2 slots. But this time I'm choosing 2, but out of how many? Good. And just multiplying. Right? 6 choose 2 and 5 choose 2. All right, let's look at this. There's going to be something cool that happens here. So Domino's, I don't know if that's how you spell Domino's. I don't know. I would never choose to get pizza from Domino's. No offense, but just not I like my New York style, not my cardboard style. They offer 9 toppings on the pizza. How many different pizzas can be made? Is it true that order doesn't matter? Right? If you have a pizza and you've got pepperoni and mushroom, it's the same pizza as if you had mushrooms and pepperoni on it, right? Whoa, my Lanta, right? These are all my different possibilities. There are 9 toppings. I could choose none. That's a plain pizza. 9 toppings, choose 1. 9 toppings, choose 2. 9 toppings, 9 toppings, choose 3. Now I'm going to do a little bit, right? You're going to think I'm silly here, but watch what I'm going to do. I'm actually going to write out the formula here. So you can imagine what's happening all the way down. And you can do this on your calculator for me. And let me tell you I'm going to tell you what you're going to get. If you don't believe me, you're going to get 1, and then something bizarre is going to happen. Hey, what's going on here? Can you see what happens? That's right. Multiplication is commutative. Look at this 36 right here and this 36 right here. This is 9 factorial on top of 7 factorial times 9 minus 7 factorial. But what is that? That's 9 factorial in the numerator, so is this. This is 2 factorial, 7 factorial in the denominator, but this is 7 factorial, 2 factorial. Oh my gosh, that's going to happen the entire time, right? There's beautiful symmetry with this. So I could literally just do these 5 and then do this sum and multiply by 2, right? If you recognize when the symmetry is going to happen. Kind of cool, right? I mean, it doesn't happen every time. I have to have that, I have to have the 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. Something else is really, really cool too. I want you to think about the fact that, and this, right, this is a very unique problem because you either, it's kind of binary. You kind of have a topping or you don't. So if you have your calculator handy because you've been doing this, I want you to tell me what 1 plus 9 plus 36 plus 84 plus 126 is, and then multiply it by 2. And you know what you get? Now I want you to do something else. On your calculator, I want you to also type that. What? What? You get the same thing, don't you? Whoa. That's kind of cool. Kind of cool. So look at how the reason why, right, this is kind of cool is to help us with this, the next problem. So Paisano's, right, different pizza place, sells only one size pizza, but claims that their selection of toppings means you have 1,000 different choices. Well, 2 to the 9th is only 512 toppings. So that's not 1,000. What's the smallest number of toppings? Got to be more than 9. Must Paisano's offer? Now I could just do guess and check on this, but again, when things get more complicated, this is what I'm trying to solve for. You're trying to solve for x, which is up in exponential land. Who gets it down? Logs, baby, logs, baby. Logs, baby, logs, baby. That was a little beatbox there. I don't know if you noticed, but I'm pretty good at beatboxing. So how do I, right? I'm going to log this side. I'm going to log this side. I think I'll do base 10 because the exponent that turns 10 into 1,000 is 3. What is 3 divided by log 2? More than 9. As I expected it to be, it's almost 10, but not quite. So if I'm dealing with toppings, I would say I'd have to have 10 toppings, right? And again, I could have done that by guess and check. Also, 10 to the 10th is 1,024, which is more than 1,000. Crazy, whack, funky, right? All right, there's combinations. So we will practice this more in our next live session. Oh, I forgot about the last one. This one is a combination with permutations. Can you see? I'm trying to decide between my 3 favorite sandwiches, but once I decide on a sandwich, each one of those sandwiches comes with 4 sides and 5 drinks, and 5 additional toppings on my sandwich. How many different meal choices do I have? So again, order, right? I have to think about, does order matter? Well, certainly look at everything I have right in purple. That doesn't matter. So I kind of have the situation I did with the pizza toppings, right? 5 choose none or 5 choose one. I have this whole, if you recognize the situation there, it's going to be 2 to the 5th. That takes care of the toppings on my sandwich, but what's the situation with going on in red? I can have my favorite sandwich, which is, I don't know, a Big Mac, or my other favorite sandwich, which is a Quarter Pounder, or my other favorite sandwich, which is a Quarter Pounder with cheese. I don't know. I don't eat at McDonald's very often, so I don't know exactly. But, right, if I choose a Big Mac here, order matters, right? I don't want the repeats. If I choose a Big Mac here, I have 3 favorite sandwiches, 4 sides, 5 drinks. I'm not going to, those are all different things, right? So I have 3 sandwiches that I can choose, and 4 sides that I can choose, and 5 drinks that I can choose, right? So those are all my different choices. It's not really order so much as just these are my different choices that I have. but I'm not going to pick through. I'm not going to pick, once I pick a sandwich, I'm not going to pick a different sandwich, right? To have 2 sandwiches and a drink. No, I'm going to pick sandwiches, then I'm going to pick my sides, then I'm going to pick my drinks, and then this is the toppings on my sandwich. Crazy. That is my last problem. I will see you in our next live session.